Hi, welcome to another video. So today I'm again using Microelectronica's EasyPic Fusion version 7. Got the Pic32 MX795512 for those that have been asking. Today I'm using the USB and UART connector up here. If you're not familiar, just plug your USB cable in here. So this is UART A. Don't forget these little top two switches here if you're using A. Next two down if you're using B. That will communicate with your board directly with the PC. For those of you using Microelectronica's hardware and software, just configure your ECU as normal and look, there we go, UART init. I've slowed this one down, 9600 baud rate. Right, for the UART terminal, that's really easy too with Microelectronica. Go up to Tools, down to UART, click. Now I've used this before, so it's defaulting there, or it's grayed out to COM5, just so I can go connect. Yours might default to COM1, so once you plug in your Fusion board you'll get a different number here. Click on it, make sure this is defaulted to 9.6 or whatever you've got the current speed set to, and go connect. Right, for the beginners, if you don't declare what type of font you're using, in this case it's Arial 13x14, which I imported. I've got previous videos showing you how to do that, how to build your own font. So I've imported this font. If you don't import a font, ran that out, it will use the system font, which is pretty small, but it works. So you get text on your TFT. But not declaring a font, your UART terminal will just give you the regular font anyway. If you import a big font and change it to color, you're still going to get the regular font over here. So today's video is going to be about character strings, character arrays, and pointers, and where to use them or how to use them. And now if you look at this simple message over here, it says Merry Christmas YouTube. Straight away, if I can disconnect so it stops this. So Merry Christmas YouTube, and then straight away there's Merry is joining the E, so there's no space. So that's the first thing to remember about character strings or character arrays. And just on this UART, it doesn't necessarily matter about a null character, but you need to put a space so that it will shift the next character along. So if we start with something simple, so anything in these double quotation marks, whether it's TFT write text, which has got to be text, or UART to write text, you've got to write text. Can't be like data, numbers, that sort of stuff. So as I say, anything in double quotation marks will be printed in the UART terminal or your TFT. So let's give this a go. Connect. Because this is in the while one, it's going to print this and then obviously this. Go to the end and then come back and do it again. Now on the TFT it's just printed this once, because the next time it comes along and prints it in the same position. Nothing has changed. But over here, because I keep on sending it to the UART, the previous string is still there. But notice straight away, Merry Christmas YouTube, and then the Merry starts on top of the E. It's because I've got no space here, so I could put a space there and then build and compile again. There we go, Merry Christmas YouTube, but now there's a space. So notice it keeps on running across the screen. Only when the screen is full up does it drop down to the next. Right, so to remedy this running across the screen, got a little note down the bottom. We use this carriage return line feed. This is specifically for UART. So if I undelete these, UART write, notice we're not writing text, we're writing numbers or data. So 13 and 10 means carriage return, means the carriage goes back to the left for the old-fashioned typewriters, and 10 is a new line, so that would run up a new line of paper for the next line of text. So UART 13 and 10, character return line feed. Program that. Now while that's printing, you think, where do you get these numbers from? So these are all ASCII numbers, as is most of this example here. So anything in single quotation marks, you're referring to ASCII. So you think, well, where's your ASCII reference? You need some sort of reference. So if you're using microelectronica software, back up to Tools, and there's the Ascii chart. Developed in the 1960s, it's come on a bit. Now I believe that all this in blue is relevant to microelectronica's software, because I know for a fact their fonts, imported fonts, haven't got 128. Well, I'm not sure when that came in. Maybe it's when Europe became Europe, but none of their fonts, to my knowledge, include this decimal 128 for the euro symbol. So my current font imported, I had to make up my own euro symbol and add it to the font. So you see, like, a space is 32. These are decimal numbers. Space is 32. S for center is 83. If we look at my example over here, so character 5 there is 32. Look on here, 32 means it's a space. Now I don't want to run ahead of myself. Anything in double quotes there, the UART terminal will print. However, if I leave this as a space, if I'm sending data to the TFT, so single quote, now the UART terminal will recognize this as a space, so it will leave a space. But the TFT will not recognize this as a space. So for the TFT, you have to put a 32. Right, so to put my character array into some context, the text and data coming from the SD card doesn't come in nice strings. And it certainly doesn't come in English, text. So when you're communicating with stuff, so let me get rid of this because we've finished with it. Delete. Delete. When you're communicating, you need to send character strings or character arrays or data arrays, whether it's an SD card, a Wi-Fi module, which you might have seen my video on, sending data and picking up data from the internet. You can't just send, nice fancy words in double quotes. You've got to start sending data or words, and they're built up of character arrays. So starting at the beginning, so my character array, I've called this character C. You can call it whatever you want. I'll jump up to the beginning. So there's my character. It's just called, so it's a char, so that's just 8 bits, which is a byte. So my byte C is made up of, it's saying here, if I reduce this down for now, it's made up of 12 characters. So that's what these numbers in these square brackets, I'm saying that C has 12 characters. Each character is a byte or 8 bits. So 12 bytes long. This just gets you into the basics of a structure of a bit of data. If in the near future, when I show you my SD card, you need to know how am I deconstructing what's coming in. So you've got to start at the beginning. So let's build a character string saying Santa Claus. So ASCII, now you know. So SANTA space, so that my TFT recognizes a space. Clause, so CLAUS. So where does the S? Why have I put an S in there? So to get you used to the Ascii chart. Tools, ASCII. So when you're writing or sending text, I put an 83 in there, so across to the 83 here means it's a capital S. And yes, you differentiate between capital and lowercase, so where's the lowercase s is 115. Hopefully that will make sense. So that's the ASCII. If you want to put hexadecimal values in here, and you don't have to keep on going to Google, just pull up Windows Calculator, assuming you're using Windows. So there's a calculator. So if I go get rid of this chart, now I'll leave that on there for a minute. So here's the Windows calculator, standard view, scientific calculator, and just for us, programmer. Wow. So notice it highlights like hexadecimal, decimal, octal, binary. So let's leave it on decimal for a minute because we want to convert a decimal number to hexadecimal. So let's start with Santa Claus, S. So it's 83, the decimal 83. Calculator disappeared, so make sure you're in decimal, put in 83, and it automatically converts that to hex. So that would be hexadecimal 53. Get rid of that. So if you're declaring a byte as a hexadecimal, 0x53, and don't forget the semicolon. So just for confirmation, so I've declared my char up here at the top, char x equals 10, char y equals 10. So that's for my TFT, so x along equals 10, down equals 10. As you see there, my char, I've just got one single character, x and y, but a char says one character, 8 bits, 1 byte, but a char, you can see here, char, data buffer, 8, or there, char, data buffer 512. So this is a string, and that's a data buffer containing 512 bytes. This string, so I can print it out on a TFT. I now know should be 7 data buffer string. That's converting a byte into 7 characters so they can be printed on the screen. So as you saw from the video the other day, an integer 65535. Well, that's only 1, 2, 3, 4, 5 characters. So each of these is a character or a byte each. So why do I need 7 here? So 6, 5, 5. Let's start from the left. 6, 5, 5, 3, 5. Well, they put a null character at the end. So that's a 0, and the number could be a sign like a minus or a plus, which isn't shown. So when you're converting to show numbers on a TFT, I'm converting my data there, just 1 byte of it, only 1 byte, converting it to a string, so I need 7 characters available to show my string. Even though this string might only be like my Santa Claus, might only be 11 long, but because it's an int, could be up to 65535 plus the null plus the sign bit, could be a negative 65,535. Hopefully that makes sense. It will do if you saw my video from the other day. Right, I don't want you to get too confused with this character name. I've called it C, but you can call it anything you want. So, for example, I've defined a char, actually twice. So char, supercalifragilisticexpialidocious, and I've said it's 3 bytes long. And then I've defined a char here, but char Z, and I haven't put in a size because the size is defined there. So, coming back down to our Santa Claus, if I just remove this null character, so this by itself doesn't make much sense and isn't of much use. But when you want to start receiving or sending data, whether it's GPS, Wi-Fi, Bluetooth, SD card, you need to tell the device, right, this is your last character, it's a null. Go back to your Ascii Chart, Tools, Ascii Chart. Look, null means it's a naught. That's what an old keyboard would have sent to the computer, meaning the string that's just been sent, that's the end of it. So you can see, where's our 10 line feed? We know 13 was carriage return, 127's delete. Have a look at the Ascii chart. So that's our Santa Claus. That's another char. So supercalifragilisticexpialidocious bit 0 equals S for Santa. A bit 2 equals N, just as an example. So you can call this char anything you want. So let's put it on the TFT write char, because we're writing a character, not a line of text. So we're going to write TFT naught, X and Y is defined above 10 and 10. So X, 10 across, 10 down. And then the same on the UART. UART to write. So we're not writing text, we're writing data. Build and compile. Connect the UART. Oh, it's already connected. Wait for this thing to boot up. It's looking for the start name on the SD card. Well, there's the S. So that's the first character of that character array. Can be anything. As I say, can be data coming from a GPS. But now all of a sudden we've located character 0. So that's not much use by itself. So if we've got 512 bits, so for example this C I've defined as, what have I defined it as? 13. Let's make that 12. I could make this 512 bytes long, but that would just cause problems. So let's make this one 12 characters long. So 11 down to 1 but plus a 0, so that's 12 characters long. So now TFT write char. Let's, instead of asking for 0 or say position 8 or 10, let's put a count. And I've already got a counter in the other part of the program, so for the TFT, as the counter increments, the letter across your keyboard will increase, from left to right. That will increment, and the count equals count plus 1, or you can say count plus plus. So let's delete that. And then, or for the keyboard, x equals x plus 20, you can actually say x plus equals 20. It's the same as saying x plus x equals. So let's delete that. So count plus plus, x plus plus. So this count is now going to start counting through these numbers. And the same on the UART. Put count. But when this count gets to the end of the string, it's going to carry on counting. And I don't know if the count is a char or an int, so it's either going to count up to 255 and go back round to naught, or 65,000 and go back round to naught. So let's put it here. So we've still got the UART write, it's a carriage return and line feed. So if brackets the count, if I just show you something in case you're not familiar, if the count is equal to naught, and I use these parentheses, I call them a then because I was familiar with BASIC. That's where I started with BASIC, not the regular C. So if count equals naught, then, oh sorry, this is wrong. So if the count equals 12, then count equals naught. So that's going to get to 12, go back round. Don't forget to close the if statement. So that's like an end if. Now obviously for the experienced ones of you who were looking at this, you know this is going to be wrong. But for the beginners, you won't know why. Well, if the count is equal to 12, that's saying the count is equal to 12. In English language, that would work. But in this language, it doesn't. Right, I was just looking at this bit here, this counter, and it wasn't very clear. It was clear as mud. If I, for the beginners, If I say the count is equal to 12, or with the if, I'm asking, but then here I'm sort of declaring. So the count is equal to 12. I may as well say the count is equal to an elephant. If this variable is already the same as this variable, count equals 0. This isn't asking anything. It's saying the count is equal to a variable, and a variable happens to be the number we want. It's not asking is it equal to this variable. It's saying it is equal to this variable. We still want the count to equal the count. And if the count has got up to 12, then we want it to go to 0. So the count, is it equal in value? If the count is equal in value to 12, then count equals 0. Take away 1 equals, we're now saying that variable is equal to 12. Just like this count is equal to 0. We want the counter to still be the counter. So if the counter has actually got up to 12, hopefully that makes a bit more sense. Well, I've missed a couple of letters. The TFT's got it. There's our AND clause. Actually, we've got a funny digit there. Right, that last bit, the UART wasn't working correctly because I had this counter before the UART. So it kept on resetting before it got back to the position 0. So all I've simply done, well, pull it all in one screen now and put that after that. Also see another mistake up here. I had this 83. I started playing about with this because I thought, what's going wrong? I had this defined as Ascii S, and I noticed over here I think I had 89, and Ascii for S is 83. Tools, Ascii Chart, 83. So that was another mistake. But so Santa Claus, null character, build and compile. So another tip about this count. I've made sure it's 0 here, and when you first declare the count as a char or int, if you don't define it as 0, that count could be, when you turn the chip off and back on again, that count could be up at 200. So until it comes back round again, you're never going to see this. So if you don't declare it as 0 somewhere, a good tip would be if the count is greater than or equal to 12. That would still work. Anyway, so now we've got our string and our Santa, S for Santa's back, because I put this in the right place. Let's now do something else. So if the count is greater than or equal to 12, now we'll take these because there's no text after it. Copy, put these in here. Control V for paste. Undelete them. So now when the count gets to 12, we're going to have carriage return and line feed, and the count equals 0. Total compile. I actually saw some junk in here earlier because whilst this was off camera, I changed the char, made it bigger, made it 15, and you're going to start getting junk. So it's important to make your character array the correct length, including one for the null character. I was just wondering, why is this coming down the screen still? It's because I didn't delete these. Build and compile. Right, so now we've got our string, which could be data coming from a GPS, or we want to send it out to Wi-Fi or something, specific Wi-Fi, and I did a video on ThingSpeak and I didn't know how to do it at the time, you've got to declare the string length that you're sending. If you have a look at the help files in Microelectronica, they're not awfully clear if you're totally not familiar. So we want the string length, but let's char text Microelectronica as an example. So it's an integer is a result. Result equals string length text. Calculates the length of the text string. Result equals 16. So anyway, working this out, I've eventually sussed. Right, you put your simple string in here, and it gives you the result. So now let's introduce that, which gave me heaps of trouble because I didn't allow enough room for the result. So for the TFT, you can just write that, but for the UART, where's my UART gone? So this is going to do all this and then get the result and come around and print it again. So if I copy this, so because I'm converting it to a string here, result, which is an integer, result string, which is 7 bytes long, it's already a string, so I don't have to do anything else with it. So result string, so press Control space, result string there, but that's going to sit it on top of the other text, so copy, let's put some spaces in here. So actually we're going to put some text. Copy that. Paste. Build and compile. Oh, that's a funny result. I wonder if it's because my result string is text. So it's underscore. There we go. So the 11 had already come up on the TFT. Actually, so now I've got those spaces. Oh, I see. It's because it's counting the characters in the array. So SANTACLAUS 1111. Oh, then it's character return SANTA. I'll see what's happened. So it's spelling out Santa Claus, but putting the length of the string in between each character. So what we can do, cut all that. So when the string gets to 12, put it in here. So we don't think we need a space that long. So one space before, one space after, build and compile. That's better. So Santa Claus is the program has already worked out using a function string length. Here is told me it's 11 characters long, and that doesn't count the null character. So let's go and check. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 over there, 11 here, so it's not counting that null. That's very important. So what's more important as well, sending data somewhere. If that's blank, it's not going to work, something's going to halt. And as I said earlier, the UART doesn't mind this, but everything else does. You can't have an empty space. It's got to be either a 0 or a character. Something's got to be there. It can't be nothing. The UART doesn't mind, but trust me, everything else does. So Ascii for space 32. In fact, now I've generated my own euro symbol, which is Ascii 128. I can put in there 128 over here. So we should get this euro symbol now for all our European buyers using the euro. Actually, that was another mistake I made, saying the euro came in when Europe was formed. No, the euro came in when they chose to use the euro. Yeah, there's our euro symbol in the middle. So now if I put a euro here, and instead of a null, 128. In fact, let's make it more complicated. So 128. Get the calculator up. Cancel. So decimal 128. Hexadecimal 80, which rings true. So let's put a hex number in here. We should get the euro symbol there, and because it's not a null, it will then be counted. So this 11 should go up to 12. So we could see so now we've increased the character length. Don't forget to increase the character array because it will freeze. If not tonight, tomorrow morning when I turn it on. Build and compile. What I've done wrong, no semicolon. Right, so Santa Claus 11 with the euro symbol in the middle. That should become a space again. We should have the euro symbol at the end. Aha! Now look what's happening. Because we've just increased our counter length, so we've got 12, but our counter here was if it's greater than or equal to 12, but now it needs to go up to 13. It's funny, it made an error there once and then not there. But notice, so adding that character, it's now including it in the count. And I added the null character after, so it didn't go up by 2, just went up by 1. I'll clear this. I cleared it at the wrong time. Right, here we are. Actually, I thought I'd put the space back there, obviously not. So there's our Santa Claus ending in a euro symbol. Ascii 128 hex 80. So that's an introduction into string and character arrays and using string length to calculate the length of the string. So just for laughs, clear this here. So we'll take this 80 back out. Naught, delete that. So whilst I'm coming back up here, put that back down to 12. Right, so that character array, superfragilistic, expialidocious. character Z, yeah, char Z. So let's measure that. What's that? 20, 30 characters. So string length of Z. Build and program. Now this is going to be wrong again because I've just cut one of those characters off, but let's see what happens over here. So that is how to use the function of the string length. It's easy once you know how, so put the name of your string in here and then there's a result. What's it called? Supercalifragilisticexpialidocious is 34 characters long. There's our Santa Claus. I've actually removed one of the characters from the end, so we've got some junk at the end of that. So I wanted to quickly explain pointers because it's one of the least understood or least well explained functions in C. So if I start first of all, A is a character and putting an asterisk in front of it makes it a pointer. So my A is a pointer. Come back down to the program. So there is my character array. So get rid of this. So when you use pointers, you're generally pointing to an address of something. So get rid of this. A, and I think it's going to be writing text. So for the TFT, we're going to be writing text A. UART write text A. I think that's all right. Don't need our counter anymore. Oh no, if it gets the counter, but don't need it really, not anymore. So that was our supercalifragilistic. So now that's going to be A. So now the length of A is going to be returned and hopefully printed on this UART. Where's my defines there? Here we are, I've copied it already, so cut that. We want this declared first here. So A is pointing to the address of C, and the address is defined by putting the ampersand there. If you don't put that, and you just have A equals C, you'll either get garbage or your system will just freeze because it will. Let's see if it compiles. Well, I'm surprised it compiles and doesn't generate any errors. So ampersand C, so A is pointing to the address of C, and at the address of C we've got all these characters. So TFT write text A, UART write text A, and then when it's up at 12 we'll get our return. So hopefully in there we'll get our length of A as well, which is string length here. So A, the pointer, is pointing to the address of C. Let's build and compile. And first of all, we're using a pointer and we've got no errors, so that's a bonus. So let me clear this. Right, so we've got our first Santa Claus, there we go. That's printing our Santa Claus, and on a TFT we've got the same, although it's going over itself. So really for the TFT you'd want to include y equals y plus 15. That will stop the text running over itself on the TFT. So if I make this counter equal, if it's greater than or equal to 1. Right, the TFT is now printing Santa Claus in a diagonal fashion, and it's printing here in a proper fashion, and this is our length of Santa Claus, 11 characters. So that's a good example of how and where to use a pointer. So now if I delete the asterisks from here, build and compile. Actually, I'm surprised it's frozen, because in previous attempts it has ran. Maybe it's because to do with the UART. Select implicit conversion of int to pointer. There, and there. Actually, it's possibly is this one here. So if I delete this, no, it's frozen. I'm surprised it's frozen. I'm not sure if it's to do with the UART, because you can normally declare or not declare a pointer, point it to something. You'll get this implicit conversion of int here, but all that is saying is the compiler is warning you that you're converting it, something to a pointer, and it does it for you. So it's possibly the UART here, because trust me, it would normally work. You ignore the warnings and it just works. But so if I make that A back into a pointer, I'm shocked that it's stopped. Let me see if I can figure it out, because it normally works. TFT write text A. Let me delete this UART, because I don't normally use the UART. Well, it's not the UART. Or it could be this actually, yeah, because we haven't got a result. I'm lost. Because normally if you don't declare something as a pointer, the compiler does it for you. So I'm obviously making an error, but I'm wary that the time on this video is going on. So if I put that pointer, the asterisk symbol back, trust me, take my word for it, this normally works whether you declared it as a pointer or not, because the compiler does it. These are just warnings, and where they say implicit conversion, it's the conversion is implied, and the compiler has done it for you. So what else did I delete? So that's right. Or UART. It's probably the UART. Or it could be I left these two bits in after deleting A. But so build and compile again. Right, let's back to how it was. So the A pointer pointing to the address of C. That's C. And that's what's in the address of C. But how do we get the address of C? Well, I prepared a bit earlier in the week actually. So I think I can use this one. So long unsigned to hex, and I want A in there. So that's converting the pointer back into an int. So we'll get a warning down here, but just ignore it. Then you could put TFT write string there. So that's the, no, we don't want that one. TFT write text out. Right, text out string, you can see there it's declared as 21 spaces. Right, text out there was declared as 21 spaces. I think this is going to go over what we've got on the TFT already, so if I delete this, I think we're good to go. So A is text out, TFT write text out, but now we want the result on the UART. So UART write. Actually, no, there it is. There, look, I've already. Right, long to string. Right, delete this one. Long to string, long, unsigned to hex. so we get the hexadecimal result here. Otherwise you'll have to convert the long number into hex, so this is doing it for us. So long unsigned to hex, so it's A to A string, and UART write text A string. But so I don't make the same mistake, we want this up here. Yeah, put it above here. Paste. Right, let's see what happens. Build, compile. Right, there's our sender clause, and there's the address at the end. And it's a long unsigned. So I think we've got 13 zeros or 13 places somewhere. So let me get rid of this first text. Well, A is pointing to the address of C. Then we're converting that A to a hexadecimal string, and then writing the string on a UART. Right, there we are. So we got rid of the nonsense text. That is the address of C. And if you saw the video from the other day, you'll see we're dealing with, I think, 32-bit numbers. So that is high address. So A001FFF0. That is where C is planted in the memory. So pull up your calculator. Don't forget, standard scientific programmer. Click on the hex. A, what is it? 001 FFF0. So we are up at 2,684,485,616. So that is a virtual address, which then refers to physical memory somewhere else. That's why the numbers are huge. So that's how a pointer works. If you point to an address, you can get the whole address or whole of the contents. If you convert it to a string, you can read the actual number of the address. Now, one warning you get down here, implicit conversion of pointer to int. When we convert that pointer back to an int, you get the warning it's converting, it's dereferencing the pointer back into a number. So you get this warning, and that this compiler is doing it for you, and it starts getting complicated if you try and dereference A and convert it back into a number, because somewhere you are coming away from a pointer and converting it back to a number. So it's hard to get rid of the warning, so you just simply ignore it. But if I take off that first A, don't make it a pointer, yet use it as a pointer, build, which one is it? That one. You can see we've got this warning back, and depending whether you're writing to the UART or TFT, I forget which, because it worked happily the other day. Without making A a pointer, it still works as a pointer because the compiler converted it for us. But to get rid of at least one warning, that should be a pointer. And that's how to use it. A pointer pointing to an address of something. So that's pointing to C. So some ready-made examples are up here. I wonder if I could point it to Z. I'm not actually checked. Should we see if the address of Z. So we've still got our warning where we're converting the pointer back to a number. There's our number and there's our pointer. So clear this. Well, you see that is a totally different address. So Z A O O O O down. You can see it's right down at 146, and that's our Z. We've still got the length. Do we still have that in string length? Yes. Oh no, result string length because A has now become supercalifragilisticexpialidocious. Our string length is now A, which is pointing to Z. So that's good. Our string length still worked. There's our 34, and that here is the physical or virtual address of Z. So if I get rid of this, delete that, delete that, delete that. So you only want long strings when you want the long physical or virtual address. So now if we go UART right, so A is now pointing to Z, UART right A, build and program, and look, all the time we're not converting it back to a number to read it here, we're pointing to an address, no warnings. I think because the UART doesn't like writing something here if it's not declared properly. I'm sure that it's the UART that was freezing earlier. So now you can see, so A, we pointed A to C, and we got Santa Claus. Then we pointed it to the address of C, converted it to a number, and got the virtual address number. Now we pointed it to Z, and got the supercalifragilisticexpialidocious. Without even writing it out, we just pointed to the address of Z. So now I think there's one other example, constant code. So this constant code means it's written in a memory. So W equals hello YouTube. So let's point to W as a last go. So look, I'm changing one letter and getting a whole different result over here. In fact, so now A points to that address. We'll get the writing over here and we'll get the length. Oh no, we won't. I've taken out the length. Hello YouTube. So as you see, so A pointing to the address of W. If you take out the ampersand, as I say, it's no longer pointing to the address, and then you don't need a pointer. Put that back in. So if I get rid of this, close that down. So I put a little note here earlier. It's actually quite, well, a little note took me ages to draw out. So this was the address of C, and you saw the address was starting with A001FF. I didn't think it was FC. Anyway, this is an example. This is a virtual address, A001FFEC. Next address, which is another 8 bits, 1 byte long. So that's ED, EE, EF, FO, F1, F2. So the addresses are incrementing in 8 bits, or 1 byte. We started at this address, and in the address was SANTA space clause. You can see I've put hexadecimal, and that's it, and it would continue, but C was only assigned to these characters or these spaces. So that's how pointers work. If you refer to an address, you can get what's inside them. If you can convert the address to a number, it gives you the virtual number, virtual memory and number. Hopefully that makes sense. In the chip itself, you won't get ASCII characters or even decimal. They're all hexadecimal. So I've given you examples here. So that's how to use pointer. So this is another good example, and the final example I'm going to give of pointers. So in this switch statement for the day of the week, this is taken from one of Microelectronica's clocks. You get the time from an RTCC, so real-time clock calendar chip, and the chip will give you a number from 0 to 6. So 0 is a number, so 7 days of the week. If it's not between 0 and 7, you get an error. So this text is pointing to, this char, text 1, is pointing to a string here, or character array. So it's one pointer pointing to 7 different items. So this is another good example, but text 1 is equal to Sunday, and it's equal to Monday, and it's equal to Tuesday, depending on the number. So because text 1 isn't text 1, it's text 1 is equal to this. This text 1 is equal to that. That's pointing to that. So that has to be a pointer. And it's declared there, little asterisk, text 1. See, it's compiled and running. Bring up the UART. Right, it's now on this, not on COM1 because I've not used it today. Switch to COM5. Connect. So there's no space between the days of the week, but you can see Thursday, Friday, Saturday, Sunday, Monday, and it runs quite happily. If I remove this asterisk, it's not a pointer anymore. Building, or I'll just build it. I won't compile because it won't run. And you can see here, implicit conversion of pointer to int. There, 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 there. So if you get this warning and your program's not actually running, the compiler hasn't done something for you, just go back to your code, look at if you've got something pointing to something else, that means it should be a pointer. Put the asterisk back. Build. So it's fairly straightforward if you've had some examples to go by. So this has got no faults here. As I say, if you're converting a pointer back to a string to show it on a UART or TFT, you will get a warning, and it's easy, just leave the warning there and just go with it. The compiler does most of the stuff for you. Only if the program halts, look at the error and go and find your pointer, or see what you're pointing to and change it to a pointer. That's simple character arrays. That's the pointers, and which I've deleted now. That's the string length. So pointers, string length, and character arrays. Hopefully that all makes sense. And the suspicious conversion here, we're probably getting that because the W is a constant code, but it's only suspicious. It doesn't matter. If you get warnings here, generally you just ignore them because the compiler does the work for you. So hopefully the video hasn't gone on too long. There's been a lot of important details, specifically pointers and how to use them, and character arrays and when and how to use them. Click like if you liked it. Thank you very much.